Welcome back to CMOS radio frequency integrated circuits. So, we have been talking about power amplifiers, and in the first lecture I thought we would cover class A, B and C amplifiers. I did not, I just managed to cover class A amplifiers. In the second lecture I thought I would cover class B, C and D amplifiers. I did not. I managed to cover B and mostly class C amplifiers. We actually just studied the class C amplifier as a generalization of class A, class B and class AB amplifiers, right. So, in the previous lecture what we studied was the class C amplifier. It is conducting during a small period of time out of the entire cycle. I have arranged the bias voltage V bias such that only during a small angle of time, small portion of the period, only during a very small portion of the period the transistor is actually on, the remaining time the transistor is off. So, this is the general idea, right. Now, first of all, this was the profile of the current going through the drain. Then we figured out what is the average current going through the drain, what is the fundamental of the current going through the drain. Now, the RF choke allows the average current to go through, everything else is rejected, which kind of tells me what is the power consumption of the circuit. The fundamental component can't go through the RF choke, right. It also can't come from the tank, because the tank looks like infinite impedance at the desired frequency. So, therefore, the fundamental component is completely delivered to the load, and therefore, I can figure out what is the power delivered to the load. So, that is basically what we did in the previous lecture, and we had two expressions, one for the power delivered to the load, best case power delivered to the load, and one an estimate of what is the power consumed from the power supply. So, with these two estimates we figured out what is the efficiency. All right. Now, we saw that the class C amplifier, as you decrease the conduction angle, the efficiency becomes more and more, and things look very exciting, but the tragedy is that you are not really delivering any power to the load. As you are improving your efficiency, at the same time you are reducing the total power that you are delivering to the load. What is the total power that you deliver to the load? It is only so much. Okay. And for a certain phi, let us say phi equal to pi by 4, if phi is, that is where we got an outstanding efficiency, right. At lesser conduction angles things are going to be even better, even closer to 100%. So, twice phi is basically pi by 2. So, it is something like 1.5, right, between 1.5 and 1.6. So, 1.55, and sine 2 phi is 1, pi by 4. So, 2 phi is pi by 2, sine of pi by 2 is 1. So, this will give me something like 0.55 times 0.55 by 4 pi times VDD times IRF, right. 0.55 by 4 pi, factor of 4 pi is something like 12. So, you have got almost 1/24th of VDD times IRF. So, the amount of power that you are delivering finally at the end of the day is also going down. So, this is the unfortunate part of the story. So, there is only so much power you can deliver. Now, in our applications, the efficiency of course is very important, but the amount of power that you are delivering to the load is also extremely important, right, because you are designing to deliver a certain amount of power to the load. So, typically what happens is at the end of the day, as far as radios are concerned, radios for cell phones are concerned, you almost never make class C amplifiers. You do not even make class B, you typically make something which is a class AB amplifier. This is more or less the accepted story, and class AB amplifier means that the conduction angle is more than, so the time during which the transistor is on is more than half of the time, but less than all the time. Now, what does this mean? Okay. So, between class A, B and C, typically class A, B is the best compromise. So, we will stop at this, and we will look at a couple of other architectures. One is the class D amplifier. Now, a class D amplifier is a kind of a push pull amplifier. The idea is this. Let us once again draw our schematic. Now, the thought is this, that if I drive this transistor hard enough that it works like a switch, if I can make the transistor operate like a switch, when the device is off, the current through it is 0. Okay. So, the power consumption is 0. When the device is on, there is current, but the voltage across it is equal to 0, which means once again the power consumed is equal to 0. All right. So, if I can operate this particular MOSFET as if it is a switch, then it is never going to consume any power. So, I have to drive the voltage at the input of the MOSFET very hard. So, this is like a square wave. All right. So, if I drive the input of the MOSFET like a square wave, when the device is on, it is not consuming any power because the voltage across the device is 0. When the device is off, once again it is not consuming any power because the current through it is 0. So, where is all the power going? Suppose on the average, or forget the average, suppose when the device is on, it is taking a current of I max. When the device is off, it is taking a current of 0. So, the average current that it is taking is, assuming 50% duty cycle, is I max by 2, okay, which means that the average consumption of power, not average consumption of power, the power consumption from the power supply, think about it, this does not allow any current other than DC. So, the current through this is equal to I max by 2, assuming 50% duty cycle. It does not really matter what the duty cycle is. So, that basically means that the power consumed from the power supply is VDD times I max by 2. Where is all this power going? The inductor does not take any power, the capacitor does not take any power, the MOSFET we just proved is not taking any power. So, where is all the power going? Where is it going? It is going to the load. There is nothing else, right? There is just one MOSFET which is not consuming any power. We just proved that it is a perfect switch. If it is a perfect switch, then it does not consume any power. Inductor does not consume power, capacitor does not consume power, the tank circuit does not consume any power, but my voltage, my power supply voltage is delivering power. So, clearly all that power is being consumed by the antenna, there is no other way, right. So, what does that mean? That theoretically the efficiency is 100%. Now, is this correct? Think about it once again. All the power is being delivered to the load. All the power is being delivered to the load. So, therefore, what I am saying is that the efficiency is 100%. There is a little bit of a flaw here, quite a few flaws. First of all, there is no such thing as a perfect switch. Okay. So, in the absence of a perfect switch, the MOSFET is going to consume power and therefore, the efficiency is never going to be 100%. Fine. Let us say that you do have a perfect switch. Does this argument hold water even then? Is this correct? Is it correct to say that the power delivered to the load has an efficiency of 100%? Well, you are justified in saying that the efficiency, that the power delivered to the load is equal to the power consumed. But is all of this power at the desired frequencies? Yes? No? What is the kind of waveform that you are going to see across the load? The spectrum of that waveform. You are going to see the fundamental, you are going to see second harmonic, third harmonic, etc., etc. So, all of those harmonics also have power in them, which means that this 100% of the power that you are delivering, you are taking some power from the power supply, translating it to a lot of different frequencies, your fundamental, second harmonic, third harmonic, pumping them into your load, all right, but the desired portion of this is the one that is at the fundamental frequency and not at the other higher frequencies, right. So, even this statement theoretically eta is 100% is kind of flawed. We have not done the Fourier analysis that we did before. We did not find out the fundamental portion of the current going into the load. How much is the fundamental portion? You can find out, it is a square wave, right. it's not terribly difficult to find out the fundamental of the current going into the load. There is the filtering action, which is why I am hesitating to do it on paper. I do not want to do it on paper. You have to include the filtering action over there, and otherwise the current going in over here is straightforward. You can find out. All right, let's just do it, right. Let's say that this is the waveform of the current going going into the drain of the MOSFET. Now, as we said before, the current going through the RF choke is going to be the average of this, which is I max by 2, which means that the current going into the load tank and load is basically going to look like this. It is a square wave of period capital T. All right. And then what we are trying to figure out is what is the fundamental component of this. How much is the fundamental component of this? I suggest that you do not go by I estimation over here and actually do a computation. So, your current, we can do actually work on the previous one. What was our okay. So, this is the fundamental component, and actually I am going to shift this a little bit. Actually, let us shift our axis a little bit. So, let us not say this is 0, let us say this is 0 and this is t, because that is really what is going to give me the correct result. All right. So, that is what I have got, and you take out I max outside the integral and you work on this integral of cos theta d theta is basically sin theta. Sin theta going from minus pi by 2 to pi by 2, sin of minus pi by 2 is minus 1, sin of pi by 2 is plus 1. So, I have got plus 1 minus minus 1. So, that is equal to 2. So, the fundamental component is really 2 by pi times I max, right. So, that is why I did not put I max by 2 over here, it is not right, it is 2 by pi times I max. Okay. So, this fundamental component is not going to go into the tank, because the tank looks like infinite resistance at the chosen frequency. So, therefore, it is only going to be delivered to the load, which means that the power delivered to the load is the amplitude of the fundamental squared by 2 times r, right. And basically you are going to get I max times VDD by pi. Right. This is the power delivered to the load, and the next step of course is to make sure that power consumed is I max times VDD by 2. So, therefore, the efficiency is basically going to be power delivered divided by the power consumed. So, you are going to be equal to 2 by pi. Okay. So, this is the unfortunate part of the story, that hey, it looked very promising when I started off, got a theoretical, seemed like I am getting an efficiency of 100%, but when you recall that the power delivered to the load has a lot of different frequency components, it is not just the fundamental, then you realize that this argument is flawed. And really, going by our previous discussions, the way we did the class C amplifier, find out what is the fundamental component of the current going into the load and what is the amplitude at the load, etc., and then you do the derivation, you will realize that the maximum efficiency that you are going to get is something like 2 by pi. The next thing is, so these are basically called class D amplifiers. Okay. You have to realize that the input to the class D amplifier is something like a pulse width modulated signal. The input to the class D amplifier is a pulse width modulated signal. What I am suggesting is that by changing the width of this pulse, you can achieve whatever signal you want, and basically your filter at the output is going to make sure that you just have a narrow band of frequencies around your center frequency. So, the class D amplifier is kind of, it's almost synonymous with pulse width modulated amplifier. You can conceive of having a sigma delta modulator as the input, driving the input of a class D amplifier, right. A sigma delta modulator is a pulse width, gives out a pulse width modulated waveform. We saw this before when we were talking about frequency synthesis. So, it is popping up in all the wrong places, sigma delta modulation, but anyway. So, you could conceive of a pulse width modulated waveform, that is the input to the class D amplifier, and power is transferred out. The catch is, you have got to remember the catch is that all the power is not at the fundamental frequency. So, beware of that. The efficiency is 100%, as long as the switch is perfect. Of course, the switch is also not going to be perfect. Okay. So, these class D amplifiers are not commonly seen in cell phones. Okay. Primarily the problem is the pulse width modulated waveform that you need at the input of the class D amplifier. So, that is a big stumbling block, especially when you are talking about extremely high frequencies. However, the class D amplifier is very popular at audio frequencies. It is very, very popular at audio frequencies because it is so easy to build, and you can conceive of having an audio sigma delta converter, which is also easy to build, and the output of the audio sigma delta A to D converter, you have got a 1 bit A to D, can directly drive the power amplifier, and you have got a pulse width modulated waveform at the input of the power amplifier, and treat it as a class D amplifier and figure out your analysis. All the power gets delivered to the load. Of course, there are harmonics and you can't avoid them. Okay. Now, in all of these amplifiers, class A, B, C, D, AB, whatever you want, we have achieved efficiency. We can get whatever efficiency we want, we can deliver power. The problem, the basic problem with all of these amplifiers is the linearity, and linearity is a very important concern, because in modern wireless systems, your system has to be very good, very linear, as in you are not allowed to transmit at channels that do not belong to you, right. Your base station has instructed you to transmit at a certain channel, you can't violate that. So, there are some terms that are commonly used. One of the popular terms are ACPR, adjacent channel, power rejection. Okay. So, this is an acronym that is used in all the standards documents, right. And so, we saw that just by a squaring operation, you basically smear the signal to twice the bandwidth, right. Similarly, of course, when you do a squaring operation on an RF signal, you actually come down to baseband and to high frequencies. So, squaring is not really the problem. When you do a third order nonlinearity, okay, you will actually see the smearing. Any kind of odd order nonlinearities will smear your signal and will give you power in adjacent channels. So, that is bad for us, and therefore, we want a perfectly linear amplifier. How are you going to make a perfectly linear amplifier? Is it even feasible under the present circumstances? So, what we have got is a power amplifier that is horribly nonlinear. Okay. Your input signal over here and the output, the relationship between the input and output is not at all linear, which means that if the input is a perfect sinusoid, your output will have a lot of harmonics. All right, we do not want these harmonics. In fact, the harmonics are not really our problem. Our problem is when the input is a sum of two sinusoids that are close to each other, then the output will have a lot of other unnecessary components that we should not have been having. So, if my input is sin f1 plus cosine f1 plus cosine f2, the output, because of a third order nonlinearity, is going to have 2 f1 minus f2, it is also going to have 2 f2 minus f1, and of course, it will have f1 and f2. Now, f1 and f2 are desired signals, but 2 f1 and f2, 2 f1 minus f2 is very close to f1. It is not something that I want. 2 f2 minus f1 is also very close to f1. It is not something that I want, right. So, this is what basically creates the problem. How do I solve this? Well, one thought is, why do not we pre-distort the signal? So, I will put a block over here that is also nonlinear. Okay. Then I am going to send it to my PA, and I am going to say that between these 2 points I have got perfect linearity. Now, such a system is very hard to build. So is a system called post distortion. So, okay, this is also very hard to build, and it is not, they might not be feasible in fact, because the PA, the characteristics of the power amplifier depends on a lot of different things, depends on temperature, it depends on the process, etc. And the characteristics of this distortion circuit, pre-distortion or post-distortion circuit will also have to change accordingly. So, the post-distortion circuit is almost never feasible, because you really want, you are really planning to drive the antenna. Instead, now you are going to drive the post-distortion circuit, and the post-distortion circuit will have to drive the antenna. So, it is really not something which is advisable. The pre-distortion is still okay as a system, but you know, it is very hard to build. What else could we do? Is there anything else that we could possibly do? Anything else that we could possibly do? Any thoughts? Well, you can think of using feedback. We have done this a couple of times. This is the general block diagram for a feedback system. Our plant over here is the power amplifier. Okay. So, if somehow I could sense the power output of the power amplifier, or if somehow I could sense the quality of the signal at the output of the power amplifier and compare it to what I want, then that is kind of going to give me a linear system, right. Feedback makes sure that the feedback is going to make sure that distortion is also minimized. Is it or is it not going to make sure of that? How is distortion reduced when I apply feedback? What are your thoughts? No thoughts. Think of this as a high loop gain system. Okay, you always want large loop gain. So, let us say this one is not linear, it is a x plus b x cube. All right, this is x is the input, y is the output. It has some characteristics that looks like this. Now, I want a total gain of a. So, I sense the output, I divide the output by a factor 1 by a and I compare it with the input. All right. And this I of course need a plant over here. I am sorry, I of course need a controller over there. This comparison gives result to an error signal. All right. And if the loop gain of my system is very large, then the output is equal to a times the input. If the loop gain is very large, then E has got to be 0, because if E is not 0, then X is going to be infinitely large. Let us say this has extremely high gain. Okay. If E is large, then X is out of range, X is infinitely large, and you can't really tolerate an infinitely large, I mean it is not, it does not make sense, right. It is never going to be infinitely large, because there is negative feedback, and therefore, that basically tells you that E is equal to 0, and if E is equal to 0, then the output has got to be equal to a times the input by virtue of this, by virtue of the feedback path. So, we are basically relying on the linearity of the feedback circuit, right. So, we can kind of it really does not matter what that polynomial over here is, it does not matter what this polynomial over here is, as long as you have got high gain over here, this will always work. What do you think? Is this conceivable? Can we do this? We could do this. The problem is with the high gain block. How are you going to get high gain at an RF frequency? right. It is hard to make a gain of 10 and you are asking for extremely high gain of infinity. It is not really conceivable to make such high gains at RF frequencies, unless we put a tuned circuit over there, right. Now, if we do put a tuned circuit over there that has extremely high gain at the chosen frequency, then that means that only at that chosen frequency is the feedback system making any sense. At other frequencies, the output can be whatever else it possibly wants to be. Agreed? So, you could make a high gain amplifier at a tuned set of frequencies, right. That is kind of conceivable, not at all frequencies. Okay. So, this is one thought, one direction of thought. The next thought is it possible that we do not deal with high frequencies, we translate this entire portion to a low frequency? Is it possible to have to translate this entire portion to a low frequency and then up convert it and then broadcast it through the power amplifier? So, what I am suggesting is why do not we build something like this? H of S is an integrator over here. I forgot to put the 1 by A portion over here. Now, what is going to happen? It is easy to build an integrator. An integrator means infinitely large gain at DC. So, around DC, the error signal over here is 0. Okay. What does that mean? That means that at DC, these two signals are equal. Okay. That means, I am sorry, that means that the output of the feedback mixer is equal to A times the desired output. Right, and that is forcing the output to be what you want. Now, this is also pretty nice. This kind of strategy is very nice. Of course, you have to make sure that make sure of a few things. First thing that you have got to make sure is the DC offset of the mixers. That is a huge problem, especially of the feedback mixer. So, you are almost never going to choose DC as your frequency of choice. Maybe you are going to choose something offset from DC by so much frequency. In that case, your H of S has to be designed to have infinite gain at that particular frequency, right, at the IF frequency. So, it is not too difficult to build such an H of S. As long as it is not DC, it is okay, it can be some small frequency. The next thing is of course, the fact that you have in band and quadrature phases, and you do not want them to get mixed up, right. So, you can modify this architecture a little bit. So, this is a modification of the previous architecture to accommodate for in band and quadrature phase. This is actually a very popular architecture as far as the transmitter is concerned. So, the signals I and Q are directly coming from a D to A converter, right, and they are little bit they are not exactly at DC, because it is hard to make the mixer, the feedback mixer function and out at direct down conversion, it is hard to make it function. So, it is a little bit offset from DC. However, you have to remind yourself that these signals are further coming from a digital system. So, it is not terribly difficult to have some small frequency over there. So, it is all very straightforward, it is done digitally. Now, this is the saving word for everything, whatever you can't do, you do it digitally, right. It does not mean that the end of the day it is really going to be easy, but anyway we are going to say that it is done digitally and we will not worry about it. So, these I and Q signals are at some low frequency, and the error signal has got to be 0, right. This error signal has got to be 0. What is even better is that this entire thing can work digitally, just that you need to build 2 more A to D converters in that case. So, it is feasible to make this entire block in the digital domain, okay, but you need 2 extra A to D converters, which may or may not be justified. So, over here what we need is some sort of an analog subtraction. It is not terribly difficult to make an analog subtractor at low frequencies. The filter, what I have termed H, it is a continuous time filter. H has to filter out all garbage, all the other higher harmonics, and it has to make sure that within the band, within the band of where you want your output to be faithful to I and Q inputs, signal passes right through. So, that is what you have to make sure when you design H of S. And then the quadrature mixer is of course something that we have studied before. The power amplifier can be a nonlinear power amplifier, it does not matter, and the rest of the system is straightforward. Now, what is of great concern over here is the mismatch between the I and the Q path. So, if the I path, you have made an H of S for the in phase, you have made an H of S for the quadrature. If these two are not identical, then you have got a problem. Similarly, you have made an attenuator 1 by A for the in phase, you have made an attenuator 1 by A for the quadrature. If they are not perfectly equal to each other, you have got a problem. Similarly, the subtraction, this particular unit over here, right. These two also have to be perfectly matched to each other, otherwise the in phase and the quadrature phase are not going to be exactly what you want. You are going to get some constant times the in phase plus some other constant times the quadrature phase, which is not what you want. This particular error is kind of broadly called, it has a term which you will see in your standards documents. It is quantified as EVM. Okay. So, it is like this. The I, this is the in phase I, and this is the quadrature Q, all right. These are the in phase and the quadrature phase phasors that we are talking about. Think phasors now. So, the phasor of the in phase is a certain magnitude, the phasor of the quadrature is a certain magnitude, means that the net signal is the vector addition of these two and the net signal has a certain magnitude and phase, all right. Now, these in your communications books you will see a constellation diagram. Suppose you are doing something like binary phase shift key, then your constellation diagram will have these 4 points. Okay. If you are doing some other modulation scheme, the more difficult, this is very easy to realize. I mean, in phase is either there or not there, quadrature phase is there when in phase is not there, etc. The other more difficult schemes are when the constellation diagrams are all over the place. actually drawn it incorrectly. So, this is called 16 QAM. Okay. There are 16 symbols, 16 possible symbols. At every instant of time, you are actually sending one of those 16 symbols. So, which means you are sending 4 bits at a time. So, it improves the data rate of communication. So, 16 QAM is used quite often in modern systems, modern cell phone systems. And so, if you have made a mistake in this phasor, if the I path has gain that is different from the Q path, so you probably wanted to go over here, but your I path, let us say, has more gain than the Q path. The Q path has less gain, which means you will come somewhere over here. Now, the decision as to whether this particular symbol belongs to this or this, if that decision is clear, then you have met your EVM requirements. If that decision is wrong, then you have not met your EVM requirements. So, the modulation scheme is kind of going to tell you what is the maximum error in terms of I path and Q path gains are concerned you can tolerate. So, the error vector magnitude is let us say this was the desired phasor, instead I have achieved this phasor. So, the error vector magnitude is this much. All right, and they will tell you what percent this can be, what percent of your total amplitude this can possibly be, that is what they are going to tell you. So, this is why matching between the I and the Q path is very important, and this is going to play an extremely crucial role in this scenario. So, this kind of feedback system, this is called a Cartesian feedback system. This is very popular in modern radio architectures. In GSM systems, the amplitude is always the same, it is a sine wave. Okay. So, you can also employ other different architectures which use polar feedback. So, instead of comparing x and y, you compare the magnitude and the phase and create some sort of feedback loop using polar feedback. So, I am not going to discuss polar feedback in the class, but you can, I will point out a reference which you can look up as far as polar feedback is concerned. Okay. So, we are going to stop the discussion over here. So, we have discussed power amplifiers, class A, B, C, D amplifiers, pulse width modulation, class A, B amplifiers. Of course, we went into the details of efficiency, how much power is delivered to the load, and then we have studied feedback as a linearization technique, right. So, thank you for your attention.